It's a real honor to be talking with you today. I'm really excited about this conference. I want to talk to you today about a project I worked on many years ago in building exactly this, web APIs for desktop applications. And there's two takeaways I want to try to impart in this talk. And in some sense, they're both very obvious, and in some sense, they're both not super obvious at all. And the first is that there's more to APIs than just getters and setters, right? So a lot of APIs out there are around accessing data, the CRUD interface. Some APIs are a lot more exciting than that and can do a lot of fun things, but I'm going to talk about an API for actually driving a desktop application. And I think if you could drive a desktop application with an API, there's a lot of things that you can do with one that have not been really adequately explored. And the second is that I want to emphasize use the right language for the job. Again, a lot of us here, I think, already know that. It's kind of preaching to the choir, but on the other hand, there's very much a culture of, I can do everything in this language. I don't really need to explore other options. JavaScript. I'm a C++ guy myself, so I see the world through C++ colored lenses, and I think it's a lot of fun. But in the real world, in production code, you got to use the right language. And it may not be your favorite language. In fact, it may be one of your least favorite languages, but it may be appropriate, and sometimes we just have to get over ourselves. So, as I mentioned, this all started some years back with Screenhero. Who here in the room has used Screenhero before, or is at least familiar with it? Oh, this makes me so happy. So for those of you who don't know Screenhero, it's real-time screen sharing for collaboration, or was. This is in a liminal state of non-existence right now. And the idea was that you could share your screen with somebody else, you could collaborate in real time on a project, and it was great. And about 2 years into the project, no, let me back up. This is what the stack looked like for Screenhero. So at the point where I entered the story, or where the story begins, Screenhero was largely a finished project, and the stack looks something like this, right? So 2 computers talking to each other over WebRTC, right, which is a peer-to-peer connection that's established between them. And we have 2 servers that support the creation of these connections. One is a server running Nginx in Rack, which is a Ruby application server that handled the private API, a lot of stuff around protobufs. It also did the corporate website. And then there's an eJabber box. And eJabber is a daemon for the Jabber chat protocol and interface, which drove a lot of the real-time communications needs that we had with Screenhero. And so we were given the opportunity to help Slack, this is before we joined Slack, to help Slack build a slash command. So you could type /hero into Slack and instantly be sharing your screen with anybody else. So has anybody in here ever seen that or tried that? It wasn't a widely advertised feature. It still works if you're on Screenhero and you're on Slack. You could do this, type /hero, and that mentions somebody, and you'll be sharing your screen with them, and it's quite cool. But the challenge for us was figuring out how to do that, and especially to do that in the context of this stack, right? And so that's what I want to talk about here today for the most part, is what the stack looked like for this, how we managed to build this sort of system, and maybe it inspires you to do something equally fun with yourself. So let's back up just a little bit and see how this sort of thing kicks off when you type /hero into Slack. So your Slack client makes a call up to Slack servers, which are implemented in PHP. So I've got this little number over here in the corner. You're going to have to crane your heads way to the left. That's the number of languages that we're going to touch in the course of this. So Slack's backend is written in PHP. There's a special file there just for handling the /hero case. And PHP, of course, is great for making HTTP connections to the outside world. And so when they approached us about making this bridge, we had to sort of accommodate what they were doing in PHP. So we had to provide HTTP endpoints for their PHP code to call. And the natural place to put this was in our Nginx /Rack server. Now, most of what we were doing on that backend was written in Sinatra, which is a really great, lightweight web framework for serving web pages. We even did some API stuff in Sinatra. But I wanted to go a step further as I built this. This is about choosing the right tool for the right job. We built the Screenhero API, the HTTP API in Grape. Grape users in the room? My kind of people. So why Grape? Why didn't I just stick with Sinatra? And the reason is that Grape is a DSL in Ruby written specifically for building APIs. It's super slick. It's really cool. Here's a complete API. Look at this. It's one file. Actually, it's not fully complete. There's a few things missing from there. But basically, it's one file, and it works quite simply. So the first thing that you do is you create a class. You inherit from Grape's class, and you get all sorts of great functionality. So you can version your API. You can say how it's versioned, whether it's in the path, whether it's in the header. You can set a vendor ID. You can set the default format. One of the wonderful things that Grape does for you is you return a Ruby type, and it figures out how to turn that into JSON or XML. And you can provide methods that will turn it into other formats if you need other formats. And it does it all automatically. It's really great. Grape is designed for building CRUD or REST-like APIs, and so it has this notion of resources, and so we built this on top of the user resource. And one of the things that you can do on top of that is you can define a set of parameters, validations for those parameters, whether they're required or optional, and Grape will handle all of the validation for you. It'll reject requests that don't have all the required parameters. It'll reject requests that don't have valid parameters. I don't want to go so far and say it's magical, but it's super handy. And then when you actually want to define the full endpoint on top of the resource, what we're looking at here is /v1/user/share, and we're doing a post to share in this case. It's just a simple matter of writing a function, right? So we have an authorized function which will throw a 4.0 whatever unauthorized if you don't have the right credentials to call the API. We have a permitted function that will also throw a 4.0, forgive me, I can't remember, a 4.0 whatever, unauthorized, if your application hasn't been authorized by the user to do things on their behalf. And then there's one method. We just call this thing called share, which is not defined here. This is why we need more than one file. That actually initiates the share. And then it just, there's a Ruby dictionary at the end. That's the return value. We fill it in with whatever we got back from share. And that's it, right? And then Grape turns that into JSON and sends it on its merry way. So if I have to build another API, I'm definitely doing it in Grape. It's really quite good for this sort of thing. So let's talk a little more about the share function. So we'll notice a couple of things. One, it's synchronous, despite the fact that we're making a whole lot of network hops, which is kind of an interesting problem in its own right, because Slack needed to know whether or not a share was going to succeed. And then there's the mystery of, well, what does this actually do? Which is the truly interesting bit. Well, what it does is it generates a bit of JSON RPC. You're going to see a lot of RPC in here. In fact, from this point forward, everything's going to be done over one form of RPC or another. I love remote procedure call functionality, right? Because this is what allows us to move beyond simple getters and setters and to begin to do interesting things. So JSON RPC is a spec for specifying what a remote procedure call should look like. And so this is a very simple example. We're calling a method called toggle sharing session, and we're passing it a JID, a Jabber ID. Very straightforward. And so this is going to get forwarded on to the clients. How that happens, we'll talk about here in just a second. And then it's going to receive a JSON RPC response back in response, and it's going to pass that back up. If you look here, the response that we get goes into retval and will get sent back on to whoever was hitting our API. So we've got our JSON RPC. We want to route it to the clients. How do we do that? Well, we're going to need to go through our eJabberD server. That means Erlang. I didn't do Erlang before, but I really love Erlang now. Has anybody in here done Erlang? Yes, no? Oh, this is a large number of you actually have worked on this. So Erlang was a language developed by Ericsson specifically to run on telephony switches. And it's designed specifically around the use case of routing messages. So anything that you need to do that involves routing messages, routing events, real-time communications, Erlang and the virtual machine that it runs on are really great. So it has some really powerful switch-type statements specifically for routing things. It has really powerful threading, much like Go, and it has this amazing feature, which is that you can hot patch it. So what this means is that, for example, at Screenhero, we might have tens of thousands of people connected to our server at any one time. We could push out an update to eJabberD, or one of the mods that we'd written for it. It gets hot patched in real time. None of the connections are ever dropped. All of our users get all of the new functionality immediately, and none of them ever see that anything even happened, which is really, really good. But the question, of course, that would be in my mind anyway, if I were you, how do you get Ruby and Erlang talking to each other? And that's actually a well-solved problem. So Erlang has an RPC mechanism of its own. It's called BERT RPC. And its implementation for eJabberD is called Ernie. And we took advantage of this. So we ran a BERT RPC server, specifically Ernie, on our eJabberD. And then we installed the BERT RPC Ruby client. BERT RPC is a type of RPC that's specifically designed for the needs of Erlang, so it packages up remote procedure calls as binary that gets injected directly into the running server, right, using that hot patch mechanism. So it's really cool. You're not just sending strings to be interpreted on the other side, you're actually calling functionality remotely using this sort of feature. So the combination of BERT and Ernie is really quite powerful when you're trying to interact with Erlang. What the Erlang does, this being eJabberD, it wraps it up in an XMPP stanza. So XMPP is the protocol that Jabber uses for coordinating messages back and forth, right? It's a real-time messaging system, and it uses XML stanzas to package all of this up, right? So there are stanzas for sending a message to an individual, there's stanzas for sending a message to a group, stanzas for joining and leaving channels, you know, any sort of chat operation you can imagine, there's stanzas for it. There's even a remote procedure call style of stanza, but it was way too heavyweight for what we needed. It has all sorts of great features like service discovery, introspection, you know, anything that a generic XMPP client might need to interact with a service, an XMPP service that offers RPC capabilities. But we controlled both the client and the server, and so we decided to go a step simpler, and we used IQ stanzas. IQ stanzas are sort of generic vendor-specific stanzas that you can use without any expectation of interoperability. And so we just made our own sort of RPC mechanism on top of this. And as you can see, we just inject the JSON RPC right in here. Then the idea is the eJabberD server knows where you're logged in when you're logged into Screenhero because you've established a WebSocket connection to the server, right? It's live, it's real time, it's two-way. We know where you are, and we can send this stanza directly to your client, and your client is going to receive it and unpack this JSON RPC. So the Erlang code that does this is actually kind of fascinating and worth pointing out for its own right. I've been singing its praises, but I want to focus on a couple of things here. So remember, this function called is synchronous. It's going to return a value, but Erlang has some really great threading primitives that make it super useful for this. So it combines the power of threads with the power of event queues. So it's got a little bit of the JavaScript model, it's got a little bit of a more traditional POSIX style model. And the first thing that we do when it receives a request over BERT RPC to send on that JSON is it spawns a thread, and in that thread it does the actual routing and sending and so forth, because it's just time intensive enough that we want to send it off somewhere else. And then we just wait. So this is very interesting. We don't put this in a message queue to be executed later. It's actually immediately being executed in a separate thread that was spawned. But then we do this thing, this receive method here, or this receive keyword says, and now we're going to wait until we hear back. Because, in fact, the response will be coming back on a different thread entirely, through a different channel. We don't know where that response is going to come from. It might even come from a different machine than the one we sent it to. That's theoretically possible. And so what we do is we say, we're going to wait until we get a message from whatever thread gets the response. And we're going to wait for no more than, you can see at the bottom, for no more than 5,000 milliseconds. If we get a response from whatever thread, doesn't matter, then we'll forward that back up to the client, otherwise we'll throw a timeout error, and that's fine. So this is a really powerful set of primitives for concurrency, which is another thing that makes Erlang and the Erlang virtual machine really great to work with for real-time and time-sensitive communications. All right, so we've routed this JSON RPC onto the client. What do we do with it on the client? Well, the client is Windows and Mac, right? So we have to support two completely different runtime environments, and we do that by building most of the core functionality into a C++ class. So now we're at language number 4, C++. And we use libstrophy and WebRTC to coordinate communications. These are great C and C++ libraries for WebSockets and for WebRTC, as you might expect. libstrophy passes that message up to us, we unpack it. This is the level at which we understand what these IQ stanzas do, and we extract that JSON RPC out, and we're going to pop this up to the user interface. The idea is that the remote procedures that we offer here should replicate the functionality that's available to the user through the user interface. It should go through the same code paths so that we can ensure that there's exactly one way to start a share and we don't end up in a maintenance nightmare. But of course, to do that, we have to pass it through a number of layers. Neither Objective-C or Swift, nor C# can talk to C++ directly. And so it requires a compatibility layer with proxy objects. On the Mac side, we use Objective-C++, which is beautiful, right? So Objective-C, you can only call C functions. You want to call C++, you have to write stuff in Objective-C++. So we wrote Objective-C classes that wrap the C++ classes at this layer. On the C# side, things have changed a lot over the last several years, but when we were writing this, the only way to do this was to use this crazy mashup language that Microsoft created called C++ CLI, which takes bits of C#, bits of C++, mashes them together, and it allows you to link in both directions. So it's like C++ with async await. It was really weird. Lots of memory issues with that sort of thing. But that was what was available at the time. Then, of course, the applications themselves are native apps, so they're written in Objective-C and C#. Now our language count is up to 8. There's one more level. Inside of each of these is a web view, and inside of those is a common JavaScript library. So we got tired of maintaining separate user interfaces in Objective-C and in C# using Interface Builder and XAML on Windows. It became quite tedious. And so we ended up re-implementing the user interface in HTML and JavaScript. And so we had a common JavaScript library to handle the user interface to keep the two different products in sync from a user perspective. And again, because this is all designed to drive the user interface, this is the final destination, right? We pass this JSON RPC all the way up into JavaScript land, where it's unpacked, we examine the validity of it, and then we execute the function and return the value all the way back down this chain through an RPC response and back onto Slack's PHP client. So from there, things proceed just as they would, as if you'd pressed a share button. We establish a link to the other computer over the eJabberD server, and then the two start talking peer-to-peer over WebRTC, and you're sharing your screen. 9 languages. This is really exciting. So it's also one of the challenges of building this sort of system, right? If you want to interact with desktop apps, you have to be prepared to talk their language in one way or another, by hook or by crook. And each language is going to have its own unique way of talking to the next language in the chain. As you can see, you also need a way of finding the desktop client, right? So it really works well when you have a real-time service that's coordinating your desktop clients, as we did in our case. And that frequently means that Erlang is going to be somewhere in this chain, being the best language for coordinating these sorts of things. Anyway, it was a wild ride. So again, APIs are more than just getters and setters. You can do all sorts of crazy cool things with them, but you have to be willing to sweat a bit for it and use the right language for the right job. We could have done all of this in JavaScript from beginning to end, right? I mean, that's theoretically possible. We could have been running Node on the back end. We could have been using, I'm sure there's a JavaScript implementation of Jabber out there somewhere. We could have written the clients entirely in like React Native or something. Well, that didn't exist at the time, but we could have done something similar to that, right? Just pop them in a dumb web container and done everything in JavaScript on the client side. But we chose not to, and it made our life quite difficult in many ways because there's a very long code path. And it's really hard to debug, which is a story for another time. But at the same time, we were able to get the best performance, the best maintainability at each layer in our stack, and this resulted in a highly performant app that only required 4 engineers to maintain. So I'm Don Goodman-Wilson. I'm the head of developer relations at Screen. I really appreciate your time. If you have any questions, I'd love to answer them.